When I talk like that, okay, I'll try. Otherwise, just backbenchers, please shout that I should take the mic. I don't like it so much, but okay, I'll try. May I start, Mr. Chairman?
Yes. Yes.
Yeah, welcome to just another excursion in the dynamics of black holes in galactic nuclei. That is a talk which would probably fit more in the Wednesday session, but I'm grateful to the organizers that you made it possible that I can give the talk still today, because I couldn't be already here on Wednesday. And so this is what I'm showing is the result of a rather diverse teamwork, and people here at the ARI, and certainly we are grateful to our sponsors. And mostly here today I will show work in the classical dynamics regime, classical dynamics of stellar systems from Peter Berzig, who is not here. And then we will turn on later into the relativistic regime, the post-Newtonian. There is Ingo Behrensen. I will show some results of his work in Heidelberg. He is here, over there. And yesterday we already talked a little bit about Nicole Pretto's work, who is related to this LISA Germany project, and trying to get then information about the gravitational waves which come from black holes in stellar systems, and we are trying to bring this all together in some modeling framework coming from astronomy, astrophysics. And also I should say I'm proud to list here some of our previous team members who are now independent on their own feet, and some are sitting here. And here is a list of the most important collaborators. Also, some of them are here. And this is another, just before I come into the middle of the matter, I'll just have a few points, just with some entertaining, some information. And so this is the information on the right-hand side. So these are announcements of upcoming meetings which are possibly of interest, because they are mainly stellar dynamics related, but in all three actually the link to physics of gravitational waves and black hole dynamics is actually becoming more and more interesting. And so this is the general thing, the modest collaboration. Maybe not everyone here in the room is aware of that. Please have a look at this. This is a worldwide informal collaboration modeling of dense stellar systems. Pete Hutt and Steve McMillan are keeping this main webpage. There are, every year there are workshops, there are schools, and a lot of events related to this modest activity. Actually, one of them is this one here at ARI Heidelberg in March, where Matt and Sverre will come as a lecturer. And the following week we will have actually a common international spring meeting of the German and French astronomical societies, aber actually the Astronomische Gesellschaft and Société Française d'Astronomie et Astrophysique. And so this is here in Strasbourg, and in both of these events we will also talk about gravitational waves. And this one on the left-hand side, maybe if you have been curious, this is just what we consider as a root of our institute in Heidelberg. This was the Grand Duke of Brandenburg, who later became the King of Prussia, and he was looking for some scientists more than 300 years ago who give him some information about the location of the Easter fest in the calendar. And that's thanks to this initiative, our institute is there. There's a long history, stellar catalogs came, but still we have some people in our institute who are responsible for the calendar. Yeah, so this is the root of this, and now we are doing also stellar dynamics, not only stellar catalogs, so computer modeling. And this is just to show you also a little bit of the life in the group, different conferences. This is also some of our friends here. But you see it all, you find yourself. This is actually the European Astronomy Conference in Yerevan last year, in Armenia, in Budapest, and this is also in Yerevan, the big table. See Gabor Kupi, who is also assigned today, and some of our tea seminar at home. So just that you see some more, not an abstract list of names, but you see some of the social life in the group. And so now we are now entering into the more serious things. And so this is a structure of what I want to show you. Hopefully I will not manage to show you all. After a brief introduction, actually, which was inspired by the discussion yesterday on the quality of n-body simulation, so I decided to spend a few slides to show you a few general aspects about this. How much do we rely on n-body simulations? What kind of material, what kind of work did we do to show this? And then we come to the classical problem, binary black holes and galactic nuclei. Last parsec problem, stalling or not stalling, and I will just present you a new aspect in this, which we have worked on recently, and then coming to the relativistic dynamics. And here, actually, gravitational wave prediction. This will be relatively small. Actually, we have a few results coming from our n-body models, and here, actually, because this talk also I give in some other environments where I spend more time on the gravitational wave detection, but I will skip this here in this round because most of us I don't need to talk to you about gravitational wave detection right now here. And at the end, we have some tools we use. Other astronomers use telescopes. We are using computers, actually special supercomputers, and this is also a part of the research, and I like to highlight this if I have time at the end. If not, I will skip this. So this is now just a glimpse, a sketch. Cannot be a complete account, but just one old and one new result I'm showing you about the quality of direct n-body simulations. What you see here is actually part of our intensive comparison we did of direct n-body modeling with statistical models based on Fokker-Planck approximation. This is some approximation which is, for example, also behind many Monte Carlo models, but we have also direct solution of the orbit averaged Fokker-Planck equation and another thing which we call gaseous models, which are actually very nice. With Pau, there was a paper in 2004 about star clusters around the central black holes, and the gaseous model also works really nice. And what you see here, on the right-hand side maybe first, is just a radius, just chosen arbitrarily one radius containing 1% of the total mass of the system as a function of time for different particle numbers. And the straight line is the statistical model, and the fluctuating line is an ensemble average of a couple of n-body simulations. And first you see the agreement is pretty good, and it's just not only the collapse here. We see here something called gravitothermal collapse. This is a purely gravitational effect. Core halo formation, core contraction, but also we see here the reversal, and this is actually due to three-body effects. Tight binaries are forming here. We don't have a black hole. If we have a black hole in the center, it's different, but here tight binaries are forming, and their interaction with the rest of the system is treated in a statistical way again, and also this process is very well modeled. And on the left-hand side, we see another plot, also Lagrangian radii containing a fixed fraction of the system, and there we have 10, and this is an n-body comparison. We have 10,000 bodies and 1,000 bodies, and we scale the time actually to the expected factor for classical two-body relaxation, classical uncorrelated two-body encounters. And then we see this is excellent agreement. So this is a proof that in the real direct discrete n-body simulation, the expected physics takes place and dominates the evolution, the two-body relaxation. Here we see a difference. This is again due to the three-body effects. Three-body effects scale in a different way, and we think we understand this. And this is just a recent result here from just December, I think, in MNRAS, appeared with my Korean collaborators. This is just a modern, just we compare some system which has some rotation, also some mass spectrum, and different tidal limitations. The details are not so important here. Just look at this is central density as a function of time measured in half-mass initial relaxation times. And here you see again the gaseous, the Fokker-Planck model. And the core collapse here, the binary activity starts, and there's a post-collapse, and there's a dissolution of the system due to the evaporation into the tidal field. And here you just can see how good or how bad it is. There are some issues I won't discuss here. One can fit more the pre-collapse phase. There are some parameters in the Fokker-Planck model with which one can also try to fit the dissolution better. There's some discrepancy, but overall we think N-body simulation is quite reliable, give quite good results in all cases we have tested so far. And yesterday we were talking about the resonances. Resonances, this is actually the most lonely place in the solar system. It's interesting for N-body people who worked on star clusters in the 90s. Now in the 2000s you can find them on two different kinds of conferences. One is gravitational wave and the other is planetary systems, planet formation. Because for planet formation we use our N-body codes to model the agglomeration and the rendezvous growth of small bodies to large bodies. And for example in the Kuiper belt we have some interesting objects in the solar system. The Sedna is so far outside, you see from its surface you will see here solar system like that. And there's some interesting question about how it come out to this orbit. And so we started, actually one of my diploma students started to model the resonances of these planetesimal objects with Neptune. And I just want to show you that we can reproduce properly resonances. This is the eccentricity actually as a function of semi-major axis for all our bodies. And we just integrate for some, I think, 50 or so Neptune orbits. And then you see here, Neptune actually is located here. It scatters some objects out, but it also collects objects here at the resonances, and they are properly staying at the resonances as you can observe actually. But the mystery is actually how an object like Sedna, which is further out here, gets out to this far remote location here. But actually, there is some improvement in the code necessary to properly reproduce these resonant orbits. If you're interested in this, I'll just talk about this when you have a question. Okay, so that was a general, just a little detour, and we are now coming to the point of the black holes, the binary black holes, the nuclei. I have here two slides from Miguel who give a nice introduction, but probably you are already well into the theme. I don't need to read every line or explain every picture. We are looking in the centers of galaxies. We are interested in the stellar system around the massive black hole. Lots of orders of magnitude to bridge. Our simulations typically are in the area of several tens to hundreds of parsecs. We are interested finally in the interaction of stars with a massive black holes and the black holes with each other on this scale here. This is actually the sketch for the single black hole, and here's another sketch for the binary black hole. This famous observation by Stefanie Kommerser, the binary nucleus in about 1000 parsec separation, and so this is actually. So we have some work on the single black hole problem, which I will not discuss here. Now in this talk I will talk about the binary black hole problem, binary black hole in a galactic nucleus, and actually this is something like the inspiration for our initial setup, which will come. Generally here, this has been also already discussed. Generally I discuss here a little bit and show you the expected number of mergers we have of different masses, and I know, Alberto, sorry, I should just replace this by a newer plot. This is actually not the most recent quantitative data, but it still suffices to give you an idea what are the numbers per year, what we expect of, for example, here the 10 to the 7, the 10 to the 9, of the order of 1, and 2 orders below, we have order of 10, let's say, mergers. Averaged all over the universe here is a function of redshift. So this is a rate per redshift per time, and when you integrate this curve, you get the rate per time. And here, just sorry, Alberto, I'll just take care to just get a new picture soon. It's more recent paper, more recent data. Now we are talking actually about this problem. Yesterday we already talked about the dynamical friction. Beagle, Langford, and Ries, I think, the first to realize this problem that we have actually in a sketchy way. Here's a time scale and here's a separation of the two black holes. In the beginning, in that sense, I was saying that the dynamical friction is not a problem. The dynamical friction time scale is mostly short enough and fast enough to bring the black holes together to several parsec, let's say. But then it stalls actually because the separation becomes smaller or comparable with the mean interparticle distance, and then dynamical friction is not efficient anymore. And we generally have to bridge quite some orders of magnitude in time scale and have to find a way if we want to merge, if we want them to coalesce by relativistic, by gravitational wave emission. There is a gap here actually, and this gap, at that time it wasn't clear how the gap could be filled. Several people started actually to work on that, including us, and now I'm showing you a few results. Several aspects how we bridge the gap. The first turn out when we look in direct n-body simulation. So this is our setup now. So now we are coming to the abstract system. And just having some coherent galactic nucleus, which is supposed to be a merger remnant, just with two black holes in a separation of about 1,000 parsec, orbiting here in the galactic nucleus. Typical parameters, something like observing the m sigma relation, or the black hole mass, bulge mass relation, but also varying some parameters. I will not go so much in the details. And what you see then, that's already from 2002. We started with Mark Hemsendorf to work on this. Basically, you see that as a function of time here, this is one time unit is about 10 to the 6 years, so this is something like 5, 10 to the 7. And this is the binding energy of the black hole. Dynamical friction here is just unbound, getting bound here. And then we see this kind of fluctuating curve. On average, the black hole actually increases its binding energy, but in a kind of stochastic way. And it was later, around that time, also understood that this is the effect of super-elastic three-body scatterings with field stars. So the stars interact with the two black holes, and on average they are kicked out with a higher velocity, take away energy, and the binary black hole becomes harder. And there are some theoretical arguments saying that this hardening rate should be roughly constant. And here it seems to be roughly constant. These are just different parameters of the simulation, different particle number. And already at that time, actually, it was mentioned by us, and also I think by other people, that there's a possibility to get a very high eccentricity. We had some runs where eccentricity was 0.9 and higher. And certainly this is the gravitational wave time scale is very sensitive to this. If we have eccentricity of 0.9 and higher, that may be one aspect to relieve the stalling problem. Yeah. This is, since we are here, I mean, since I'm not in such a hurry, I hope at least not yet, maybe later, I just give you an impression really what's the motion of the black holes in the system. It's just to give the eye, instead of showing a movie, just here you see something. This is the initial phase. Sorry for those who can't distinguish red and green. This is green is one, and red is the other one. This is before they become bound, actually. Yeah. And here, this is in the phase the black hole binary is already bound with a high eccentricity. Yeah, you can see the eccentricity here from the nature of the orbit, and you can see the kicks, the recoil of the center of mass of the object in the nucleus, which comes from these interactions. Yeah. So this is. Now this is the bottom line of the results we published in 2005. Also other people, the bottom line, collecting many runs, not only these, also going to more than 1 million particles actually. I show later the plot with even higher n. Finding was that when we now go to very long time scales, we see that there's a saturation actually. In the beginning everything is the same, like one would expect from this first theory, which I said. And then as a function of n actually, for small particle number, this is 1 over a, sorry, this is 1 over the separation of the black hole as a function of time. So here it goes relatively fast, but when we go to larger and larger particle number, the rate of hardening of the black hole stalls. It gets slower and slower. So we were back at the point saying, Well, this doesn't work. Purely stellar dynamical processes don't bring the black holes together. There is indeed the Stalin problem. Despite of the three-body scatterings, they don't help. They bring the black holes maybe one order of magnitude closer together, but it is not sufficient. The reason why this happens is actually the loss cone. I'm not sure, maybe on Wednesday it was already discussed a little bit. When we start our system, we're looking here at the loss cone. This is a kind of poor person approach to the loss cone. Certainly one has to do it in a more proper way, in phase space. But just roughly speaking, the loss cone is a region of phase space at a certain distance from the binary black hole, where the orbit, without any further perturbation, will just lead to a close interaction with the binary black hole. And these stars are in the beginning, all these stars are there, we speak of a full loss cone, and so they can all interact with the binary black hole. They are kicked out and ejected from the center of the galaxy. And in this phase, we have this full loss cone. There we have this constant relation, 1 over A is proportional to T, just from an n sigma v style argument, constant hardening rate, we say. And as long as the loss cone is full, and this you see in the beginning, that all the curves for different n fall on top of each other. But when the loss cone gets empty, we come into the diffusive regime, where 1 over A is proportional to time over the particle number. That is what we have seen then, this leveling, when n goes to very large particle numbers, as for galactic nuclei, actually the hardening rate goes to zero. It becomes dramatically smaller, and the reason is the loss cone is empty, and we need stars to diffuse in angular momentum space here by some process. And the process is generally first assumed to be two-body relaxation, so therefore the 1 over n, this is coming from the two-body relaxation. However, if there exist other processes, like the keyword is resonant relaxation, that may accelerate the process. Yeah? So we have another idea, but this summarizes the picture, what I have explained now before I come to the new aspect. So 1 over A as a function of time. First, dynamical friction phase and full loss cone phase. I should write here also full loss cone interaction, so no dependence on ends. Then three-body encounters with empty loss cone. There is a stalling, high n has a small hardening rate, and here we try to reach this regime, which appears still difficult. But now, the point is, all these models, all other authors also, which we are working on that field, use spherically symmetric systems. And I continue to tell people over many conferences in star clusters, in galactic nuclei, yesterday in the discussion, that the spherically symmetric system is of probability 0 in real astrophysics. So whenever you have a system and when you have a collapse and anything closer to reality, it will not be spherically symmetric. Yeah? Even if you have a gravitationally radiating binary and it approaches a circular orbit, even in the very late in spiral phases, it may have a small deviation from circular orbit, which is important for the waveforms. The true spherical symmetry is a fiction. And so we have to think and to study the effects, going one more step actually here to axisymmetry. Axisymmetry is also fiction, but one better way towards reality than spherical symmetry. So we started actually to use our models, which we use for globular clusters, where we have some rotation, some differential rotation in the galactic nucleus, and then again puts the two black holes inside. There is some parameter which is the dimensionless rotation rate, this little omega, and this you will see in the plots. And actually the largest rotation we have is 1.8. This is something like I think 20% of the total energy, of the total kinetic energy in rotation. Sorry, I'm always walking here. I should just, anyway, it's okay. No, it's okay, thank you. And now what you see here is actually the surprising result. We have again 1 over A as a function of time. Now for the rotating model actually, I think for the 1.8. And the surprising thing, also for us it was a surprise, that you see there is very little independence here. So the 25,000 body system has a hardening rate very similar to the 400,000 body system. And I think, sorry, yeah, I'll just show you, I have some movie to show you about that. Here I will show you the final result that was published in 2006. So here you see now on top of each other, spherical case, the stalling problem, 1 over A is a function of time, and here's a rotating case. There is up to 1 million bodies actually. We see no stalling observed. 1 million body system hardens as quickly as the low-end system in the spherical symmetric case. And this is actually, I would say, not fully understood yet. It has something to do with angular momentum diffusion in non-spherically symmetric potentials. And another aspect is actually bar formation. And I'll just show you a little movie. This, not this one, here. So what you see here is a view of our flattened system with the 2 black holes which are red here, and we see it from 3 different perspectives. And here's a plot where you will see a line which shows a separation. And I now start this. So what you see here is that the black holes are rotating with the rotating stellar system, and then you see some transient bar structure forming here. And in this bar actually, which is the black holes quickly come together and come to something like a separation of 0.1 parsec, even a little bit less, with a very high eccentricity. And the bar, I mean, for those working with gas in galaxies, it is quite well known that the bar actually helps quickly bringing material together in a triaxial potential. You may say, okay, I understand the bar, that's fine, but I'll tell you the bar is not the whole story. We even have models without the bar where we prohibit the bar formation, and still they show hardening independent of particle number. So this is still ongoing research, what is going on there, but that actually encouraged us now to go ahead. Actually, I have here some models of triple black holes, but I will skip this. This is quite interesting for getting very high eccentricity, but we'll stay now with the 2 black holes. And I'm now coming here to the treatment, to the relativistic post-Newtonian treatment, because that was just the point when we say, okay, here in this kind of rotating systems, even in a realistic scaling. Pardon? Oh yes, thank you. Even with a, yeah, you could otherwise see what is coming. Even in a realistic scaling for realistic particle number and galactic nuclei, we will get in a reasonable time to the point where relativistic corrections become important. And what we are doing, well, there's a some funny comment here, I have to put it inside. So the first thing you could do is just look at the post-Newtonian, the Peters and Matthews, where you have here separation of a type binary as a function of time. And you see the shrinking here, which can be in a very, not very simple, but it's clear how to do it. And actually we did one more step. Actually, we used the full post-Newtonian up to 2.5, the acceleration. So in the 2-body system, here we have the relative acceleration between 2 particles. Newtonian is a 0 order, and then we have the 2 orders of peri-astron shifts, 1p and 2pn, and the first dissipative radiative term, the 2.5pn. So whenever 2 of our bodies come close together, we just apply this additional, close enough together, we apply this additional force. And in this part we are working together with the inner group, Schäfer and Gopakuma, and but this one actually is from Blanchet's paper, yes, it's here. And then, well, this is another view of that. Now, that here one can see how it's actually working in a test setup with Gabor Kuppe and how we had the first test simulation published. Here is a 2-body system. You see the shrinking with time. Here is a sketch where one can see the variable shifts, and it's all working properly, I think. Here's a nice example. Now in the test simulation, we started with 1,000 black holes of 1 million solar mass. We just put them together in a very dense cluster just to see what happens. And there's one example where we have a very nice spiral in radius in units of Schwarzschild radii as a function of time, and one of our binary guys here really make it to the relativistic coalescence. In this paper you find a few more fancy things, but I will now turn to the galactic nuclei. This was Ingo Berendsen's task actually to continue the so far Newtonian simulations and just add for the binary black hole now the post-Newtonian forces. And what we then see here, actually we start actually at this point when the binary becomes bound. Its function of time is again 1 over A. And here you see the picture up to about 1000 in 1 over A. This is just a classical result which we have seen before. And now you see here just out of the simulation, just we come to the relativistic merger. There's some difference actually, whether we use only 2.5 pn or the full sequence of pn. There's also a difference depending on the initial setup of our n-body system. I just want to show you again here. So this is the semi-major axis as a function of time. And here this is particularly interesting. This is actually the hardening of the dA dt of the semi-major axis as a function of time. And what you see here is actually the measured hardening rate here in our system. And this is what Peters and Matthews would give. So this is what the post-Newtonian terms give. And what you see here is actually the superposition of the two effects, the three-body scattering, the effect of the environment, and the relativistic dynamics. And we have here a regime where they are both about of equal size. So that means both play a role. The black hole binary is permanently perturbed by external encounters, but also the relativistic corrections already play a role. And this is a very important regime because we only can simulate this with our direct post-Newtonian treatment. And now, then finally here we go into the final plunge. And this is, the paper is actually, I am the reason for the delay. I have it on my desk and we want to submit it this Sunday, hopefully, or Monday. And this is now the result of a large collection of simulations, merging time, logarithm of the merging time as a function of some initial eccentricity at the time when the binary becomes bound. And here is something like 10 to the 8 years, and here is 10 to the 7 years. And 10 to the 8 years is something like a good time that we have. If we make the merger in 10 to the 8 years, then we have a good chance to merge before the next galaxy comes in. And the blue is here actually the scaling for galactic nuclei, and we have several cases. The bottom line is there is a fraction of galaxies which make it in 10 to the 8 years in a fully self-consistent way to the relativistic coalescence. It all depends now on many parameters where we are working also in this LISA project. Miguel Preto actually is the guy that working also on the initial varying in a link to cosmological simulations, varying the parameters in an educated way, I would say. And this is now, thank you. And this is now from Miguel Preto's work. This is now a sketch of a few. We only have a few, and we only have equal mass, and we are now currently heavily fighting to increase our database. So these are just the first preliminary results. These are our binaries as they come from the full simulation and just start merging, and then actually the phase when three-body scatterings and Peters and Matthews hardening are about of the same importance, then we are somewhere in the pulsar time and back, just very low frequency. But shortly later, they enter into the LISA band. And what you see here is this LISA sensitivity curve and then different modes of our binary. And actually, from looking at the sequence of modes, actually, I hope that Miguel can answer some questions to this, but you can actually see that the binary is initially eccentric from the structure of the modes. Here is actually eccentricity over frequency, and you see that we come close to the LISA band in a rather eccentric way, and enter still with some remaining eccentricity. This is for the low mass black holes, more something like intermediate mass black holes. When we go to the 10 to the 6, we have already more circularized. but as Goku stresses, even if we are circularizing nearly completely, we still have a dependence of the waveform on the remaining eccentricity, and therefore we are working now with Goku and Schäfer. Our means not our, but Goku and Schäfer's waveforms, and we try now to integrate this in our apparatus. This is not yet done. We have our orbital developments and evolution of the orbital data, and the idea is now to collect a reasonable sample in a cosmological volume relevant for LISA, for example, and then superpose and create these waveforms. This is actually then part of the Jena group here, but we have this link, and this is now what is now the future work. As I said yesterday, the most interesting in my view here, also in this community, will be to include the spin orbit dynamics, which is feasible. Miguel already has some toy models with post-Newtonian spin orbit interactions, which is again a little bit tedious but straightforward how to do it in a post-Newtonian, and it can be included again, and so we have then a tool to follow also the spin evolution of the black holes. And yesterday we have heard about this semi-analytical fit formula. The question which remains for me is when actually and how can we switch to this formula, because we have some time where there is this superposition of classical interactions with stars and post-Newtonian interactions. So this is our present work, and now the computer games, the special hardware. How can we do this? This is actually not trivial, and it's not just getting some supercomputer time and doing this. These huge n-body simulations are a real challenge, and we are somehow in the tradition of Konrad Zuse, who built his first freely programmable computer in the flat of his parents, actually. So fortunately, we have the Astronomisches Recheninstitut, so we don't need to build the computer in our home. So this is actually our team in the GRACE project, where we have a computer cluster, only 32 nodes, but every of the nodes is equipped with accelerator boards, which make it as fast as 50 nodes. Yeah? So the whole thing has a sustained performance of 4 teraflop, and we are currently planning the next step, actually a 10 times scaled up version, which should go into the 50 teraflop regime and allow us to get even closer to the real particle numbers in the nuclei. And we not only need supercomputers, but we also need super software. For the experts, I'm just mentioning this. It's our n-body code is based on the R set. On R sets, n-body codes, high accuracy, special treatments for close hierarchies, 2-body, 3-body regularization, triples, quadruples, there's a stability procedure for Martling, Rosemarie Martling, and now certainly with the general relativity, the post-Newtonian. So this is one piece of the special hardware. This is what is still currently doing the most workload. These are these great boards developed in Japan, in Tokyo. Each card accelerates gravitational force computations between particles by a factor of 50 to 100 compared to what we could do on the host. And this is our second platform. This is locally developed in Mannheim near Heidelberg. This is an FPGA platform, a programmable hardware here, our MP-Race-1 board. This is a programmable chip. There we can change our force law. The development cycle of the board is much faster. We can do molecular dynamics. We can add gas dynamical forces, which are physically also important, as we have heard yesterday in our discussions. This is the design of our new MP-Race-2 board. And here's a software implementation. And this is the final thing I want to show you. So this is now the most recent development. That actually fast graphics cards are becoming available, and the companies who produce them produce also software interfaces to do numerical computations with the graphics cards. This is just a benchmark where SMBH forces actually, where we see that presently the GPU card, so this is particle number from 1,000 to 1 million, and this is just the time for some part of the simulation. Here's the graphics card is the fastest. This is our MP-Race-1 board. this is what we get on the Pentium Xeon CPU, and this is logarithmic scale, so a factor of 10. But I should say this is an unfair comparison because this is the old MPRACE board with the FPGA, which is a few years old. The new FPGA, which we will get soon, will be probably somewhere below here. So there is some competition, some race, and but many people in the world are now planning computers with graphics cards, and that is, I think, yeah, our most important tool. And I will just finish with this slide, saying that we will go on in that path to do the direct n-body simulation, link this with the relativistic dynamics and the gravitational wave generation as close as possible. As I said, the spin dynamics is what we have in mind now for the next steps, and certainly producing more data and providing them for the LISA community. And, okay, with that I will finish. Thank you very much for your attention.